Hi, I'm Shuichi Hirahara, and I'm going to present a characterization of average case complexity of pH by worst case metacomplexity. There are two mysteries of complexity theory. One is average case complexity of pH. For example, one of the central open questions is whether pH is hard on average. Another mystery of complexity theory is the complexity of computing time-bounded Corollary complexity. This question is often referred to metacomplexity because it asks for complexity of complexity. One of our important open questions of metacomplexity is whether it is hard to approximate pH oracle Corollary complexity. The origin of these questions dates back to around 1980s, but we didn't know the relationship between these questions. What we show in this work is that these two open questions are actually completely equivalent. More specifically, we establish a link between average case complexity and worst case metacomplexity. We prove that the following two statements are equivalent. One statement is average case hardness of pH, and it is denoted by dist pH is not a subset of average P. The other statement is a statement on worst case hardness of metacomplexity, and it is denoted by gap MINKT with pH oracle is not in P. How we should interpret this result? From a metacomputational perspective, previously we didn't know the complexity of gap MINKT with pH oracle. Our result classifies the complexity of gap MINKT with pH oracle as a distributional pH complete problem. From a perspective of average case complexity theory, our result provides new proof techniques of analyzing average case complexity by using metacomplexity. As a specific application of our proof techniques, we will present a hardness amplification theorem for pH. In the rest of this talk, I'm going to first review the notion of average case complexity and then metacomplexity, and finally I will present a full version of our result and I will give some proof sketch. Let me start with the notion of average case complexity. Usually, we measure the performance of an algorithm by using worst case complexity. But unfortunately, worst case complexity might not be able to reflect the practical performance of an algorithm. The reason is that we might not be able to generate worst case inputs, and therefore we might not be able to encounter a worst case input in practice. In order to remedy this issue, in the theory of average case complexity theory, we analyze the average of the running time on inputs generated efficiently from a sum distribution. Specifically, we consider a decision problem L and a distribution D, and we would like to analyze the average of the running time on inputs that is sampled from a distribution D. We say a pair is a distribution problem, and the goal is to measure the average case running time for solving a distributional problem. So the goal of average case complexity theory is to decide whether there is an efficient algorithm that can solve L on random instances generated by D. In order to make it precise, we need to clarify the notion of efficiency in the sense of average case complexity theory. In the theory of average case complexity, we use the notion of average case polynomial time algorithm as the notion of efficient algorithms. In the original definition of Levin, average P is defined as the class of distribution problem that admit an algorithm that can solve L on every instance, and the expected running time of the algorithm is bounded by polynomial in a certain sense. But recently, it is more common to use an equivalent notion of errorless heuristic scheme. An errorless heuristic scheme takes a parameter delta, and we require that the algorithm output the correct answer or a special failure symbol bottom. We require that the failure probability is at most delta, and the running time is at most poly of n by delta. We use the notation average sub delta p to denote the class of distribution problems which admit errorless heuristic schemes with failure probability fixed to delta. What kind of distribution should we consider? Usually, in the theory of average case complexity, we focus on efficiently samplable distributions. Efficiently samplable distribution is a distribution which is equal to the output distribution of some randomized algorithms. And we consider distributional NP, which is an average case version of NP, and it is defined as the class of distributional problems such that L is in NP, and we consider a distribution on it which is efficiently samplable. Now I'm going to present a landscape of average case complexity theory, and I'm going to present some of important open questions of average case complexity. So this is a summary of the slide. I will explain this one by one. First, let's take a look at these two statements. This statement means that NP is easy on average with respect to every samplable distribution. It is easy to see that if NP is easy in the worst case, then NP is easy on average as well. So we have this trivial implication. And the converse direction corresponds to a central question in the theory of average case complexity. Specifically, this blue implication asks whether we can prove the equivalence between worst case and average case complexities of NP. We can also consider a similar question in the case of pH. Recall that pH stands for polynomial time hierarchy, and pH is a generalization of NP. In the case of worst case complexity, it is known that the worst case complexity of NP is equivalent to a worst case complexity of pH. So we have this equivalence. Currently, one of the important questions about the average case complexity of pH is whether it is equivalent to worst case complexity of pH. So these two open questions are important questions about average case complexity and worst case complexity. Another important open question is what is called hardness amplification. Here, this statement means that the NP is easy on a small fraction of instances. Recall that this statement means NP is easy on most inputs. It is trivial to prove one direction, but proving the converse direction corresponds to what is called hardness amplification. Namely, assuming that NP is easy on a small fraction of instances, can we show that NP is easy on most inputs? In other words, is it possible to amplify the success probability? This is the question of hardness amplification. We can consider a similar question in the case of pH instead of NP. Another natural question about average case complexity is the relationship between one-sided error and errorless heuristic schemes. Let's write average superscript 1p as a class of one-sided error heuristic schemes. Namely, we don't allow any error on negative instances, but we do allow error on positive instances. A natural question is whether, assuming that there is a one-sided error heuristic scheme for NP, can we show that there is errorless heuristic scheme for NP? We can consider a similar question in the other setting, like low success probability regime, or in the case of pH. So this is a summary of a current landscape of average case complexity. In this work, we established this implication. Specifically, we proved that if pH is easy on a small fraction of inputs in the sense of one-sided error heuristic scheme, then we show that pH is easy on most inputs. As a corollary, we show that these four statements are all equivalent. What's interesting about this is that its proof is based on a meta-complexity theoretic characterization of average case complexity of pH. So let's review the notion of meta-complexity of time-bounded column complexity. One of the meta-complexity theoretic problem is called MINKT, which was introduced by Kelly Co. Informally, this is a problem of computing the time-bounded column complexity of X. So this is a meta-complexity theoretic problem in the sense that MINKT asks for complexity. More formally, in this problem, you are given a binary string X as well as a time bound T, which is written in unary. And the task of MINKT is to compute the T time-bounded column complexity of a string X. Recall that T time-bounded column complexity X is defined as the minimum size of a program that can print X in time T. We can consider natural variants of MINKT. For example, for any oracle A, we can consider an A oracle version of MINKT, which is denoted by MINKT superscript A. In this problem, you are required to compute the A oracle T time-bounded column complexity. Here, A oracle time-bounded column complexity is defined as the minimum size of an A oracle program that prints X in time T. We can also consider an approximation version of MINKT, which is denoted by gap MINKT. In this talk, I'm going to use order log n approximation, and the task is to compute an approximation value R of time-bounded column complexity. Now we can define gap MINKT with pH oracle, and we say that gap MINKT with pH oracle is in P if for every pH oracle A, gap MINKT A is in P. Now what's known about MINKT and its variant? Well, it is easy to see that MINKT is a problem in NP, or more generally, if you take an oracle A, MINKT with A oracle is a problem in NP with A oracle. One of the central open questions on meta-complexity is to prove NP completeness of gap MINKT, in the sense that if gap MINKT is in P, can we show that NP is easy as well? In fact, it is also open question to prove NP hardness of gap MINKT with pH oracle. Even if we consider gap MINKT with pH oracle, currently we don't know how to prove NP hardness. Probably you might wonder why this is not trivial, because the notation suggests that NP should be reducible to gap MINKT with pH or NP oracle, but we don't know how to prove such a result. Let me explain the relationship between open questions on meta-complexity and average case complexity. On the top half of the figure, I'm going to write statements on meta-complexity theory. And on the bottom half of the figure, I'm going to write statements on average case complexity. This is the same figure as before. And if we assume that P is equal to NP, it is easy to observe that gap MINKT with pH oracle is easy because it is a problem in pH. And the converse direction corresponds to the open question that I mentioned in the last slide. Namely, this question corresponds to NP hardness of gap MINKT with pH oracle. In the theory of average case complexity, one of the important open questions is to prove the equivalence between worst case and average case complexities of pH. What we showed in this work is equivalence between average case complexity of pH and worst case meta complexity of pH. As a consequence of this theorem, we can show that these two open questions are equivalent to each other. Previously, these two open questions are studied in a different sub-area of complexity theory, but our result established the equivalence between these two open questions. Now I'm going to present a full version of our result, and I will give a brief proof sketch. We can prove that a lot of statements are equivalent to each other. For example, we can show that pH is easy on average if and only if MINKT with pH oracle is easy on average. This statement means that MINKT with A oracle is easy on average for every pH oracle A. More formally, we need to consider p-sampleability distribution, but for simplicity, I'm going to omit p-sampleability here. For the statements on meta complexities, we need to consider every pH oracle A, but actually we don't have to consider every pH oracle A. For example, we can take a canonical sigma kp complete problem, which is called sigma k sat, and we can show that the statements are equivalent to a statement saying that gap MINKT with sigma k sat oracle is easy for every constant k. We can modify a success probability of errorless heuristic scheme, and we can prove an equivalence. For example, let's consider errorless heuristic scheme that succeeds with small probability, and consider a statement that MINKT with pH oracle is easy on a small fraction of inputs. Then we can show that this is also equivalent. We can also consider a one-sided error heuristic scheme that succeeds with small probability, and we can still prove the equivalence. We can also prove a similar statement on pH, error equivalent. Moreover, we can prove that average case hardness of pH is equivalent to the existence of pH computer of heating set generator. We can prove that a lot of these statements are completely equivalent to each other. Now let me explain the proof idea of our result. In order to do that, I'm going to take this specific implication, which corresponds to errorless hardness amplification theorem for pH against deterministic algorithms. Specifically, assuming that pH is easy on a small fraction of instances, I'm going to show that pH is easy on most instances. So the goal is to prove this implication. It is easy to prove the converse direction, so if we can prove the red implication, we can get an equivalence. What's interesting about the proof is that the statement we prove is a purely average case complexity theoretic. But nevertheless, the proof goes through the notion of meta complexity theoretic statements. How do we prove that? Well, first, let's observe that if pH is easy on average, then MINKT with pH oracle is easy on average as well. So we have this implication. And then we use the proof techniques developed in our previous work, which presented non-black box worst case to average case reductions. And by using these proof techniques, we can prove that the worst case complexity of MINKT is equivalent to average case complexity of MINKT, which establishes this implication. And then we go back to average case complexity theoretic statement by proving distributional pH hardness of gap MINKT with pH oracle. This is based on our previous work on unexpected hardness result for Kolmogorov complexity. So this is the proof idea of errorless hardness amplification theorem for pH. What's interesting about the proof is that it goes through meta-complexity theoretical notions. A natural question is whether we can simplify the proof by just using the notion of average case complexity. But it seems that meta-complexity appears to be quite essential. The reason is that this pH hardness is shown by average case to worst case reduction, and we can't regard this as an average case to average case reduction. So it is quite essential that we go through the notion of worst case meta-complexity. To summarize this work, we have established an interdisciplinary link between average case complexity and meta-complexity. We have provided a new proof technique of analyzing average case complexity by using meta-complexity. We believe that this approach is quite promising, and at the very least we were able to prove a hardness amplification theorem for pH by using meta-complexity. Let me mention one interesting open question. Can we prove that gap MINKT is distributional NP hard in this sense? The reason why I'm mentioning this open question is that if we can prove this open question, we get a hardness amplification theorem for NP. Thank you for your listening.